Hello everyone. So, as I told you in the previous lecture that most of the differential equations, those are associated with or coming from the real life phenomena or some real life process, do not possess analytical solution. So, hence we require numerical methods to solve such differential equations. So, numerical methods give an approximate solution, that is, it will not give a closed form type of a solution that y is a function of some x. Okay. No, it will give you the value of y for the given x or where you want to obtain your solution. Suppose I am having an initial value problem y prime equals to f of x y and y 0 equals to x 0. So, I am having like this y prime equals to f of x y together with a condition that y at x naught equals to y naught. Suppose you want to calculate a solution at x equals to x 1 and which is your x naught plus h, where h is a small number. Now, so it means by a numerical method I will calculate the value of y at x equals to x 1 and that will be a numeric number. Okay. Here we are having two types of numerical methods. One is called single step and the another one is multi-step numerical methods. In single step numerical methods we use just previous the value for calculating the value at next step, just the previous step only. Okay. However, in case of multi step we use many previous steps, more than one previous steps. So, for example, suppose I want to calculate the value of y at x equals to x 1. So, here I will use some value of y of x naught here. So, if I am using only value at x naught, then it is a single step method. However, suppose I want to find out y at x equals to x n and I am using y at x n minus 1 then it is a multi-step method. In the next, including this and next couple of lectures, we will talk about we will do some single step methods and in the final lecture we will take a multi-step method. Now, in this module we will take few numerical methods, for example, Euler's method, Runge-Kutta method and then a multi-step method to solve ordinary differential equations. So, in this lecture I will talk about Euler's method, but before going to Euler's method, let me introduce a semi-analytical method which is called Picard's. So, what is Picard method? So, Picard's method of successive approximation can be given like this. Consider the initial value problem dy over dx, that is f of x y and y at x 0 is y naught and the domain of x is x greater than x naught. So, integrating the differential equation 1 from x 0 to a general point x, I can, and using the initial condition y at x naught equals to y naught, I can write y x minus y at x naught equals to integral x naught to x f of x y dx. So, the solution of this particular equation is obtained in an iterative manner according to the scheme that y at n plus 1 iteration or the n plus 1 approximation of y will be y naught plus x naught to x f of x and y x in nth iteration into dx, where n equals to 0, 1, 2. So, for example, you want to calculate the approximation of y in first iteration. So, it will become y 0 plus x naught to x f x y 0 dx. You want to get second iteration of this or second approximation, then it will become y 0 plus x naught to x f x y 1 dx and so on. So, since the solution is obtained as a function of x, the difference between two successive approximations will also be a function of x, because in each successive approximation you will get a function of x. Hence, the accuracy of the solution will depend on the value of x, and the solution obtained will be valid for certain range of x. Okay. If you want to obtain an accuracy up to, let us say, some delta number, delta order of delta, it will be valid for a particular domain of x. It may happen that this particular solution is not valid for some other domain for up to given accuracy. So, this particular equation is called Picard's iteration formula, and as I told you, it is not a numerical method, it is something like between numerical and analytical methods. So, I can say it semi-analytic or approximate analytical method. So, let us consider this particular problem and we will apply the Picard's method onto this example. So, I am having example as dy over dx equals to x plus y. So, it is a quite popular example and you will find this example in many books. So, here y 0 equals to 1, that is initially x is 0 and the value, initial value of y at x equals to 0 or value of y at x equals to 0 is 1. Now, y 1 is given at y 0 plus x 0 to x f of so here f of x y is x plus y, this particular number, because my original problem is y prime equals to f of x y. So, y 1 equals to y 0 is 1 plus x 0 is 0, 0 to x f of x y. So, initially, so x plus initially y at y equals to 0 is 1. So, it is 1 dx, and let me write it 1. So, it is 1 plus x square will become x square plus 2 into x 0 to x, and it is coming 1 plus x square upon 2. Now, the next iterate of y is given as again 1 plus 0 to x f of x dx. So, this will be 1 plus, now it will become x plus 1 plus x square by 2. So, 1 will become x plus 2x, so x square plus so it will be when I am putting x this and when I am putting 0. So, it will become 2 plus x square plus x 3 by 6. So, we will move in this way. Sorry, it will be 1 because 1 is outside of this. So, if I put the value 0.1 for x, y1 is coming 1.105, while y2 is coming 1.110167. Then I calculate y3. So, y3 will again 1 plus 0 to x fx y2x dx. So, after putting all this, I am getting 1 plus x square plus x cube upon 3 plus x raised to power upon 24. So, when I put x equals to 0.1, I am getting y3 as, that is the third approximation of y at x equals to 0.1, 1.110337, while it was in the second approximation, second iteration, it was 1.110167. So, it is correct up to third decimal, third place after decimal. If I take one more iteration or one more approximation of y, then I am getting this particular expression for y at fourth iteration, 1 plus x square and so on, and at x equals to 0.1, it is coming as 1.110347. So, up to 5 decimal places it is correct, and it is given as 1.11034. So, this was a semi analytical method, but now we will move to pure numerical methods, and in the category of pure numerical methods, the very first method we will take a very simple method, that is called Euler's method. So, consider again the same initial value problem, y prime equals to f of x y, y x naught equals to y naught. So, using Euler's method, we will determine the numerical approximate values of the unknown function y at point x, those are larger than x naught, means after the initial point. So, if h be the step size, distance between two consecutive points, that is h, and all points are uniform, we are assuming here. So, my x1 will become x naught plus h, x2 will become x1 plus h, that is x naught plus 2 times h, and so on. So, by Euler's method we will find approximations of y at all those xi, like x naught is given. So, x1, x2, xn like. So, in that way we can find the value of y in a given interval at some uniform points. So, we start with x naught, and then we will calculate y1, then from using y1 we will calculate y2, using y2 we will calculate y3, and so on. So, the initial value problem, that is f prime y prime equals to f of x y, y at x naught equals to y naught, tells us that f of x y is basically nothing but the slope of tangent line to the solution curve at point x y, because it is dy over dx equals to f of x y. So, at the point of tangency, tangent line to any curve remain close to the at curve. So, the given initial value problem is well posed with initial value of y at x naught, and which is known to us. So, now we will find approximate x1 at y, approximation of y at x equals to x1. So, the equation of basically what we are having, suppose, and this is the solution curve. So, let us say the value at x naught equals to 0, it is given. I want to find out it at point 1, at point 2. So, at this point I will let me make it more smooth. So, this is the tangent line at x naught y naught. So, at this point this will be my numerical solution y at point 1, where the exact solution is this one. Now, again at this point I will try to approximate the value of y at x equals to 0.2. So, it will go like this. And so on, while the exact values are these values. So, this is the idea of Euler's method. So, mathematically we can write that the tangent line at x equals to x naught is given as y equals to y naught plus x minus x naught y prime x naught. Thus, approximation to the value of the solution at x equals to x1 is the y coordinate, that is x equals to x1 on the tangent line. So, y at x1 is given, that is approximated value of y1 is given by y0 plus x1 minus x naught y dash x naught, and as I told you, this particular approximation is valid only when x1 is very close to x naught, means I am having a very small h, very small step size. If I take a large step size, let us say I am having value at 0 and I want to find out at, let us say 0.5. So, I will take a tangent here and tangent line will go there. So, my original solution is this one, but I will get this one as the approximation. So, I will get more error if the step size is large. So, once we calculate y1, that is basically y naught plus h times f of x naught y naught from the tangent line, we will calculate y2. So, y2 will become basically y1 plus h into f x1 y1. Similarly, y3 will become y2 plus h times f x2 y2. So, I will get a sequence of iterations. In general, y at any point x I plus 1 is given as yi plus h times f xii yi. Now, what is the error in this approximation? Because from this figure itself you can see this is the error in my this approximation. If I take the large h, this is the error, this is the error at second point, that is when x is 0.2 and so on. So, how to calculate a bound on this error? So, for this we will use Taylor series method. So, the value of y at x naught plus h. So, x naught plus h basically x1. So, the value of y at x1 can be obtained by the Taylor series approximation of y about x0. So, y x0 plus h is y x0 plus h y prime x0 plus second order and higher order terms. So, let me, because if you see this particular thing, first 3 terms, the left hand side term and 2 right hand side terms of this expression, this equation, it is my y1 and it is y0 plus h f of xy. That is the, this is the Euler's formula for approximating y1 from the x0 y0. So, it means this is the error term r. So, here r is the remainder term and it is given h square by 2 y double prime xi, where xi is somewhere between x naught and x1. So, the error term is r, it is h square by 2 y double prime xi, that is r times h square by 2, because we know that dy by dx equals to f. So, d2y over dx square means y double prime will be f dash. So, I can write it as f dash xi. So, how to calculate f dash? Because f dash, f is a function of x and y is a function of again x. So, f dash will become f of x plus f y into dy upon dx. So, I am writing, and again dy by dx will be f. So, f prime will be fx plus fy into dy over dx. So, fx plus fy into f. So, the error term as I told you will be h square upon 2 f prime xi y, finally this particular thing. So, let us take an example and we will solve this example using the Euler's method. So, here we are having our initial value problem as dy over dx equals to 1 plus x into y square. So, here my function small f of x y is 1 plus x y square. The given initial condition is y at x equals to 0 is 1, that is y 0 is 1. Now, I need to take a step size h equals to 0.1 and I need to calculate the values of y1 and y2. The value of y1 is the value of y at x equals to 0.1 and the value of y2 is the value of y at x equals to 0.2. So, if we compare this given problem with the standard form of initial value problem, then my f of x y is 1 plus x y square. I need to calculate y double prime x, that will be d2y over dx square, that is d by dx of f of x y, and it becomes del f over del x plus del f over del y into dy over dx. Del f over del x is given as y square and del f over del y is 2xy into y dash, and y dash again 1 plus xy square. So, y double dash x is y square plus 2xy into 1 plus xy square. Why I am calculating this? Because in the question they are asking to compute error terms also, and for that I need y double prime x. Now, let us take the first step and calculate the value of y1. So, here x is 0.1. So, y1 is y0 plus h times f of x0 y0 by the Euler's formula. Y0 is given as 1 plus h is 0.1 and f of xy is 1 plus xy square. So, it will become 1 plus x naught into y naught square. X naught is 0. So, this term becomes 0. So, 1 plus 0.1, it is 1.1. Now, if I compute the error, epsilon 1 is given as h square upon 2 into y double prime xi, where xi is somewhere between 0 to 0.1. So, y double prime xi is f prime xi, and I have already calculated this. So, this is 0.01 upon 2 into this is the expression for y double prime. So, maximum truncation error is 0.01 upon 2 into 1.1 whole square, because this is the value of y1 plus 2 times 0.1 into 1.1 into 1 plus 0.1 into 1.1 square. So, after simplifying this, we are getting the maximum truncation error in y1, that is given by epsilon 1, and the value numerical value of it, this is 0.00728. Now, I will calculate y at x equals to 0.2, that is my y2. So, y2 is y1 plus h time f of x1 y1, that is 1.1 plus 0.1 into 1 plus 0.1 into 1.1 whole square. So, please note that for calculating y2, I am taking the values from the previous iteration or previous step. So, my x1 is now 0.1 and y1 is 1.1, which we have calculated from x0 y0. So, after simplifying this, I am getting this value as 1.2121. So, my y at x equals to 0.2 is 1.2121. The truncation error in this step is given by epsilon 2, that is epsilon 1 times 1 plus h f y x1 y1 plus h square upon 2 into y double prime xi, where xi is now between 0.1 to 0.2. So, I have substituted all these values here and then this term. So, maximum truncation error will be given by this particular expression plus this is for the second term of the epsilon 2, and after simplifying it, I am getting this value as 0.0179. So, here my y1 is 1.1, The maximum truncation error in y1 is 0.00728 and then y2 is coming out as 1.2121 and the maximum truncation error for this y2 is 0.0179. Now, if we take another example, that is if f is x plus 2y, the problem is same, y prime equals to f of xy and y0 is 0 here. So, if I apply Euler's method with the step size 0.25, suppose I want to calculate value at 4 points between 0 to 1, that is at 0.25, at 0.5, at 0.75 and then finally at 1. So, value at x1 x equals to 0.25, that is y1 is given by this one and it is coming out to be 0. At y x equals to 0.5, y2 is coming using the Euler's process as 0.0625. Similarly, when x3 is 0.75, y3 is coming at 0.21875 and finally at x4 equals to 1, x equals to 1, y4 that is y is coming out 0.515625. So, the true solution of the initial value problem is given by this particular expression and if I calculate the values at 0.25 by the Euler's method we are getting 0, but from the exact solution it is 0.03780. By the numerical Euler's method at 0.5 I am getting y as 0.0625, while the exact value at 0.5 is 0.179570. And similarly, we are having big errors at x equals to 0.75 and x equals to 1 also. So, it means the Euler's is having large error when compared to the exact solution. And what is the reason behind this? The reason is step size, because here we are taking step size as 0.25. If you decrease the step size, error will decrease and it happens always in Euler's method. However, you have to do more calculations. So, if we shrink the step size, we will get more accurate solution by using the Euler's method. So, with this I will stop this lecture, I will end this lecture. So, today we have learned Picard's method and Euler's method. In the next lecture we will talk more accurate method when compared to the Euler's, means one modification on the Euler's method and then Taylor series method, means we will consider more, means like in Euler's method we are taking only term up to first order in Taylor series approximation of y at about x0. However, there we will take more like second order term also, so that error will reduce. So, we will talk about those methods in next lecture. Thank you very much.